Now we want to check on the electrons themselves because they really give chemistry to an element. So how are they arranged in an atom? If you recall, Thomson thought that they were like raisins embedded within an atom, and Rutherford just said, hey, they're outside the nucleus, but I don't know how they're arranged. Well, the first person to come up with an idea about that is Niels Bohr around 1915. Bohr thought that the electrons might be arranged around the nucleus just like our planets are around the sun. So he called his model the solar system model. And this is the model that most people are very familiar with. Here's an example of his model. If we have a nucleus, we would have electrons occupying the first level. Now that level has different names. You can call it a shell. You can call it an energy level. You can call it an orbit. So Bohr thought that the first energy level could contain 2 electrons, but no more than that. If you had more than 2 electrons in an atom, you'd find more of them then in the second energy level, which could contain up to 8 electrons, but no more than that. So the first energy level is filled, and then you would move to the second energy level. Now once the second energy level is filled, you'd go to the third energy level, and the third energy level could hold up to 18 electrons. So the more energy levels we have in an atom, the more electrons that can be held there. Now Bohr reasoned that elements that had the same number of electrons in their outermost energy level have similar properties. So let's check out his ideas with the periodic table. So here's group 1A. I pulled out lithium and sodium and potassium. Here's lithium with 3 protons, atomic number 3. It would have 3 electrons. So Bohr would take those 3 electrons and put 2 of them in the first energy level and 1 in the second. Here's sodium with 11 protons. It would have 11 electrons, and according to Bohr, be broken down like this, 2, 8, and 1. You notice that both lithium and sodium are ending with 1 electron in the outermost energy level. Now for potassium with 19 protons, that means 19 electrons. Would it go 2, 8, and 9? Because the third energy level could hold up to 18. Well, not if Bohr was right on elements having the same number of electrons in the outermost energy level having the same properties. So we know that lithium and sodium and potassium have the same chemical properties. Therefore, potassium can't end like that with 9 electrons. It has to end like this. So let's step back for a second. Lithium has 2 energy levels, 2 and 1 for electrons. Sodium, 3 energy levels, 3, 8, and 1. Potassium, 4 energy levels, 2, 8, 8, and 1. So as we go down the periodic table, we're looking at these periods differing in the number of occupied energy levels. Now let's check out group 2A to see if it maintains the same pattern. Elements in the same family have the same number of valence electrons. Here's a term you want to make sure you know. Valence electrons are the electrons in the outermost level only. He thought that determined the properties. So for the alkali metals that we're looking at right now on the screen, they would all have 1 valence electron. So now we go to period number 2, and I'm just picking out 3 elements that are in group 2A. We have 4 protons for beryllium, electrons 2 and 2, magnesium with 12 protons, 12 electrons, 2, 8, and 2, and calcium would be 2, 8, 8, and 2. So notice they have 2 valence electrons. So this only works for the A groups. The number of the A group will give us the number of valence electrons, and that can be very handy when we do some bonding. It doesn't work for the transition metals, unfortunately. So we're going to see later on, near the end of the course, another atomic theory that will explain how those electrons are arranged. Now if we check out the first 18 elements, we can see how the number of electrons are being added to the different energy levels. So the first energy level is filled once we get to helium. The second energy level is filled once we're at neon, and then the third energy level, go back there, the third energy level is filled with argon. So you notice that the noble gases all have filled outer energy levels. And that's the key to explain why they're not chemically active. Now here's our basic periodic table again. And the same thing is giving you the names of the elements. And I just wanted to note that if we wanted to know the number of valence electrons, let's say for calcium, Over here, calcium has 2 valence electrons. Or if we want carbon, carbon would have 4 valence electrons. 6 electrons altogether, but 4 electrons in this outermost energy level. That would be the same for silicon, 4 electrons in this outermost energy level. Oxygen would have 6 electrons in this outermost energy level. Bromine, number 35, 7 electrons in this outermost energy level. So it's really handy to be able to use the periodic table for this. Let's take a second then, and I'd like you to take these 3 elements and determine how many electrons are in each of their energy levels. So you might want to pause right now and just write down your answers, and then when you're ready to resume, hit the resume button. Now here are the answers. Oxygen 2 and 6, silicon 2, 8 and 4, and chlorine 2, 8 and 7. 6 valence electrons, 4 and 7 for these guys. One of the things we're going to use in bonding is called an electron dot symbol. And I thought this would be a good place to throw it in. Electron dots are used to represent the valence electrons only. And if you go across, let's say from lithium towards neon, you notice that we're adding 1 more electron all the way across. And we kind of view the elements as having electrons in 4 corners. So you notice that we don't start pairing up the electrons until we reach 5. So if you look at carbon with 4 dots, and you look at nitrogen with 5, you notice that nitrogen, there's a pair of dots and then 3 unpaired. Until we get to neon, which has all 4 unpaired. So the normal order that we go in would be like this. 1, 2, 3, 4, and then 5, 6, 7, and 8. We're not going to have any more than 8 of these dots ever around an element, and that's just going to be with the noble gases. So here is the noble gases, only group of non-reactive elements. And if we check out their electrons, you notice that they all have 8 valence electrons, except for helium, but at least helium's energy level is filled. And this gave rise to a theory in bonding called the octet theory. 8 electrons in the valence level makes an atom stable. So what we're going to say is that elements are trying to achieve 8 electrons of their outermost energy level by either losing, gaining, or sharing electrons with other atoms. This is the first of our bonding theories. So atoms can form octets by losing, gaining, and sharing valence electrons. In the first example, we have a metal and a nonmetal. Metal is M, nonmetal N, M. And that metal is losing an electron to the nonmetal, and then you notice that, here we go, you notice that now the metal has a positive charge because it lost an electron. It now has 1 proton whose charge isn't being offset, and then we have a nonmetal has a negative charge. Now once we have charges formed on these particles, they're now called ions, and then because the charges are opposite, they stick together forming an ionic bond. Now 2 nonmetals, though, can share their unpaired electrons, and this winds up giving them a covalent bond. Now, you notice that there aren't any charges here, so not really transferring electrons like we did with the metal and the nonmetal. So metals lose electrons when they become ions. Now here's an example of sodium. If you look at the screen, sodium has 11 protons and 11 electrons, so its total charge is 0. It's neutral. It would have electron dot symbol with 1 dot representing this electron here. Now if the electron is lost, now we wind up with 10 electrons versus 11 protons. So the charge of that 1 more proton is shown here. Now we always write the charges in the upper right hand corner. You notice that we didn't write a 1 next to the positive. So just putting positive means a positive charge. And you notice that we have 2 and 8 for its electron arrangement. This is just like neon. So the sodium atom becomes much more stable by losing an electron than by having it. Sometimes that seems wrong to people. You think there's something neutral, but something neutral is not as stable as something that has a charge, but it's just the opposite in nature. In fact, the only form of sodium we find in nature is sodium ions. Now let's try this with magnesium. If you look up magnesium on the periodic table, I want you to answer that question. How many electrons do you think magnesium will lose? Well, it turns out magnesium is going to lose 2 of them. You notice that it has 2 valence electrons, 2 dots in its electron dot structure. When it loses 2 electrons, it's going to wind up with the same electron arrangement as neon, and then again it becomes more stable. So we can do a couple of things here. Number one, we can figure out how many electrons will be lost by a metal. It's going to try to become like its closest noble gas. The more electrons it loses, the greater the positive charge it gets. Now mostly metals lose 1, 2, or 3 electrons. You're not going to find them losing any more than that. What about nonmetals? What about chlorine here? Will it lose again electrons? Well, let's look at electron arrangement, 2, 8, and 7. It could either lose all 7 of those or gain 1 electron, so that 7 could become 8. And gaining 1 electron will be a lot easier than losing 7. So that's what it does. It gains 1 electron, and because it has 1 more electron now than its protons, it has a negative charge. And you notice that it has an electron arrangement now that's similar to argon. So chloride, notice there's a name change. Chloride is more stable than chlorine. So chloride is the ion with a charge of -1. Chlorine is the neutral atom, very chemically active. Now here's a periodic table showing you all the different charges for these ions. You notice for group 1, they all have +1 charge. That can be handy to know. Now positive ions are called cations. And so group 2, they're all +2. The transition metals, we're going to forget those for a while because they don't show that. On the right-hand side, then, we have group 3, aluminum, gallium, indium, +3. And then group 4, we really don't have ions with group 4, but we see these negative ions, or anions, in groups 5, 6, and 7. And notice how the charges go. -3, -2, -1, and the noble gases, of course, would be 0. So it's handy to know what these charges are, because we're going to have to use these symbols and charges in writing formulas later on.